So, hello everyone. Is My name is Shekzat Kudera, and I'm going to present a paper named "Robust Contract in Continuous Time" that published in 2016. My presentation involves 5 sections: introduction, set up the model, and robust contract, assess pricing, and lastly, or finally, summary. Let's see what's the story behind this paper. A robust contracting problem. Try to transfer the uncertainty from the agent, what we so called it principle, to another party. Actually, from the party, it's called it principle to another party, what we called it agent, as much as possible. So the main question is we know to ask how to design the robust contracts under the hidden action in a continuous time framework or environment. So this question, actually the paper is, so the goal of this paper is to study this question, so it will be answered in section 3 in details. Now, we also face 2 issues while solving the robust contracting problem. First, we have to consider which party faces the model uncertainty, and second, how to model the decision-making under ambiguity. The answer of first equation, it is natural to assume that the agent knows the output distribution chosen by himself, and due to lack information, we can assume that the principle faces the model uncertainty. And so the second equation, actually a popular approach is to adopt the so-called the maximally expected utility model. Here we assume that the principle deals with the uncertainty model. Uncertainty model by designing a robust contract that maximizes expected utility in worst-case scenario subjected to the agent's incentive and constraints. Incentives and participation constraints. Now we will try to ask ourselves why the continuous time framework is important for this module. Actually, there is some point I listed here. First, it allows us to represent the belief distortions by participations of their term of the Brownian motion by using the Gathona theorem. And a second is allow us to adopt and enlarge the Martigan approach to the dynamic contracting problems. And third, it is allow us to express the solutions in terms of the ordinary definition equations that can be solved numerically, which had the huge impact in economic. So the conduct last item, it allow us to conduct the capital structure implementation, and we can analyze the impact of the robustness on the asset pricing. So now we will try to set up our model. First, we consider the time infinite horizon environment and an agent on a project that can generate a cumulative cash flow process YT. So the initial capital that generates a cash flow process, but he doesn't have the financial. But he needs a financial support. So in this case, he needs, but he don't have a financial. So, but he needs a financial support from outside, let's say from investor or the principal. So the principal will provide the project an initial capital K, which is non-negative, which is a positive amount, and the agent can effect the project by action or effort level IT between IT belongs to uniform compact interval 0, 1 and dy and dyt and dy and dyt it's a cash flow. It's a dynamics of the cash flow that consists of the def term and volatility term or the diffusion term. And DBA, it's a standard Brownian motion on a filtrator probability space that consists of the states of variable and filtration, and PA is a probability measure with respect to effort level. So the agent derives the private benefits from the action AT. This will be, and where lambda between 0 and 1. So in this case, both the principal and the agent are really natural, and the discount the future cash flows for both. For principal is R and for agents it's gamma. So in this case, to get a project start, the investor or the principal offers an initial capital in exchange for a fixed contract. We say C tau A. So our aim is now to solve or to find this fixed contract. So where C is described the competition C, and tau is the terminal stopping time, and A is the effort choice or action, can be defined as the following. C and A are adapted to the filtration, which is adapted to filtration, which means that they can access all the historical data from time 0 to time t. And this all right continuous with lift limits and increasing process that satisfy the square integrability condition. This help us to use the Martinger representation theorem. Yes. And now we define the agent continuation value WT at time t. It's defined as the expectation utility under the probability measure PA is the integral from time t to tau, and the exponential of minus the future discount cash flow of the agent, and the dynamics of the fixed contract plus the private benefits. And also the expected utility at time 0, which can be defined as W0 or W0. So we can now sum our setting in so-called benchmark model. Here, the utility, the principal maximums his expected utility without considering the model uncertainty first. So it will be maximums under the maximum with respect to the fixed contract, which we have to find it, and expected utility under the the probability measure PA, so it's also integral from 0 to t to tau and exponential the discount future of the principal and the dynamic of the cash flows and dynamic of the fixed contract plus liquidated value. Actually, we didn't define L so far, but we didn't define all yet. But as we defined our project, there is also possibility that the project can be liquidated or can be unsuccessful. In this case, the principal obtain an arbitrary amount, say L, and the agents get an agent get the payout outside payout value outside value 0. So on this equation is subjected to so-called incentive constraint, and whenever this is bigger than this, we can define whenever this condition holds, the agent can participation, the contract, and the contract can get started, and we called it, and we equalize then this equation to continuation to the agent continuation value at time 0, which is a non-negative bulk amount, and this equation outside is called the participation constraint. So now we define the principal value function f b of omega 0. B is regarding to benchmark, and we remove it when we generalize our model. So the project can be founded whenever the maximum of the value function bigger or equal than initial capital. In this, here we have two cases. Actually, the principal removes this maximal. The principal removes this maximal such that the principal value function equal to the initial capital when the agent has our bargaining power due to competition of the principals, and the case 2 if the principal has our bargaining power due to the competition of the agents. In this case, the principal pay to the agent this amount W star such that this solves our value function, the maximization of our value function. So now we will define the model ambiguity. All distorted beliefs are described by jointly absolutely continuous measure with respect to probability measure PA. Then we can now safely use the Gathona theorem for changing measure, and then the model in this case is only about the diffusion term, the diffusion term, the depth of the diffusion process. So now it's important to state the Gathona theorem. So let L be a mutually absolutely continuous probability measures. Then we define a real valued process H such that as a density generator associated with the effort process A, such that satisfying the integrability condition, which is help us to use Martingale property. So we define ZT as exponential of the stochastic integral term minus the integral with respect to time is actually Martingale, or It's martingale, yes. And HA is the set of the all density generator. Then we can now assume that by Gattoni theorem, there exists an equivalent probability measure QA on this measurable space omega F, such that the random dichotomy ZT is satisfies this condition, yeah, with respect to original probability measure. In this case, we can now define a Brownian motion under equivalent probability measure as this equation. So as we have a new or an equivalent probability measure QH, we can define also our dynamic process, our cash flows dynamic process under this equivalent probability measure. Yes, it will define all the following. Just before we have dBA, here instead of dBA, we put this equation that's by Gattoni theorem. Now we try to know the deviation between two probability measure, the equivalent probability measure QH and PA its original probability measure can be defined in this equation. Moreover, the multiplier utility of the principal preferences can be defined as the infimum under the H, which is H and expected utility and expectation with respect to equivalent probability measure QH. It consists of exponential of the discount future. It consists of the dynamic process, and this term actually it's model uncertainty or model misspecification, or moreover penalize the belief distortions. So the utility, it's rational utility actually. It's also called it a continuous time version of the dynamic version utility model. And theta is a parameter theta, we also don't know yet. It's actually non-negative parameter describes as a degree of the concept for robustness or the ambiguity aversion parameter. So where theta is small implies that the larger degree of the ambiguity aversion. And when theta goes to infinity, this equation reduced to our last equation, which means this term goes to 0, and we also get this term. Now we reach our robust contracts. So the robust contract problem with the agency can be defined in this equation. It's the main equation or main problem. We have to solve it. It's subjected to equation 4, which was the incentive constraint, and equation 5 was the participation of the agent, and equation 6 was ZT, random dichotomy derivatives. So first we try to solve this equation without considering the equation 4. In this case, we called it the first base contract, in which principle observes the agent if for choice. So solving this equation, we follow a process of the 5 steps. We apply a Gattoni theorem and martingale representation theorem, since we have the jointly absolutely continuous measure, and second, the square integrability condition satisfied. And step 2, define the principal utility. And third, to define the value function of the principal and continuation subjected to the continuation value of the agent. And four, we apply the E2 lemma to the value function, then take the expectation. And lastly, we obtain our Hamilton-Jacobian-Billman-Ising equation, which is satisfied the first condition, the first order condition and second order condition, and lastly we get optimality for contract. So let's start solving. First, we define the continuation value of the agents in equations 2. We obtain this equation after we apply the Agassonov theorem and Martingale representation theorem. All this term we know so far except phi. Phi actually is a process that we obtain when we apply the Martingale representation theorem. In finance, we say that it's a market price we see in the assessed prices. So step 2, we define the utility principle in equation 3 under the equivalent probability measure. Yes, and can be defined as the dynamic of the cash flow plus the mesh specification, the model mesh specification, and we substitute dy under the equivalent probability measure. We obtained a new equation, or we get a new utility for the principles. Yes. And now we define a value function for the agent continuation value, then use the dynamic programming principle theorem to get the approximated Billman equation. And we can now write safely here, which is the dynamic of the cash flow here, and plus this term is the discount expected capital. So here, this is called the main return required by principle. On this term, it's called the total expected return, the expected total return, the expected total return. So the optimality requires this to satisfy. Yes, the main return equals the expected total return. And for we use the E2 lemma and we derive from equation 10 to derive. We use the E2 lemma and equation 10 to derive this amount, this discount the expected capital. After we found it's a partial definition equation, yeah, and we substitute it here. So we get a new version of the equation 11, can be the following term, which is actually it is a partial definition or partial definition equation, or what we so called it a Hamiltonian Jacobian Billman equation. Now we can safely remove this time subscript and dt. Moreover, we can set the dynamic of the fixed contract as Ct dt, which is a positive, it's non-negative amount. Then this is our AGBI equation. Now we have two possibilities to solve this equation. First, with respect to H, and second, with respect to phi. But we have to, we should first solve with respect to H, otherwise we will not obtain a finite solution. So we will explain later at the end of the section. So C is positive if and only if the f prime or the derivative of the value function is subjected to the continuation volume equal -1. And we define now a new parameter, which is W bar. Actually, it's a lowest level or boundary level or payout boundary, such that this f prime of w equal -1. So the principal payments to the agent whenever w bar the continuation value reaches its boundary payout boundary. So now we derive the first order condition with respect to h, and we obtain this equation, what we so called the worst case density generator. It's play important role in this paper. And second, we substituted back in our previous equation, which is h here. We substituted here. We obtain this equation. Now we solve this equation with respect to phi. We obtain, which is satisfy the second order condition. Actually, the second order condition is satisfied. Yes, it's concave, and phi can be defined as the optimal sensitivity. Yes. And now we reach our first proposition. We consider the first best contracting problem as a previous, and we subset this condition, which is liquidation. It's dominated by this amount. We consider this equation to avoid a liquidation or liquidation. So, and there exists a twice continuous differentiable solution f to the ordinary definition equation on this compact interval. And our ordinary definition equation can be defined as the following. So with the boundary condition f of 0, f prime of w bar, and f double prime of w bar, yeah. And such that we consider the second order condition holds true, and also f prime of w bigger or equal than -1 of this interval. Then we have two cases. First, if the continuation value belongs to this compact interval, we consider first the value function of the principal and optimal sensitivity and worst case density generator and effort process A star of W equal 1 at optimal level. So the contract at beginning pay a non-negative value to agent whose continuation values follow this dynamic with the initial condition, and the optimal payments are given by this equation. By this equation. Moreover, the project is never liquidated, which is amazing. And second, if the continuation value is above the payout boundary, the principal value function can be defined as this, and the principal pay this amount, as we see, to the agent directly, and the contract continues with the new initial value of the agent. So as we see, we don't have too much time to prove it, but we will try to explain the idea behind this proposition. As we see, the principle is ambiguity averse, and try to transfer this uncertainty to the agent while designing a contract, and the agent is risk neutral and ensure the principle by making the principal payoff loss constant. That's follow from the Martingale property. Third, the contract is not feasible due to the limited liability. And third, the cash flow can be negative. In this case, the agent faces the losses. And fifth, with the limited liability, the uncertainty is limited. And sixth, we defined a new condition, what we called the net marginal cost to the principal from delivering or from obtaining additional value from the agent, delivering from delivering additional value to the agent. It's 1 plus f prime of w is bigger than minus 1. So, and the principal make payment if and only if this marginal cost condition satisfy at payoff boundary w bar. So, lastly, there is a trade-off following. On the one hand, the principal want to make earlier payment to the agent because he's impatient. On another hand, principal also want to delay a payment to get the agent continuation value get a bigger. Now the robust contracts with the agency. In this case, we consider our equation 4, which was the incentive constraint. What this case called it the case with the molar hazard, in which a principal doesn't observe the agency for choice. We set this condition, and our goal is also obtain a GBI for optimality. We follow the same five previous solution process steps. Beside that, we consider as said the constraints, the incentive constraints, and setting 82.1. So the HGBI can be written as the following. Yes, it's it's a partial definition equation, and worst case density is the same, and the boundary, payout boundary is the same, and C is positive whenever the f prime of w prime equal -1, and C is equal 0 if f prime of w bar bigger or equal than -1 for the continuation value between 0 and w bar is not inclusive. So we put in equation 13 in 23, and we obtain our Jacobian beam HGBI for robust contract with the agency under the condition 15, which was the worst case, the worst case density generator, and optimal sensitivity phi can be written as a maximum between these both guys, and these terms describe the model uncertainty. And if theta go to infinity, this optimal sensitivity reduced. This will be 0. This will be the optimal sensitivity amount. So now the following proposition characterize the robust contracting with the agency, what we so-called it the verification theorem. It's somehow the same as before, except with some tiny change. And we consider the robust contracting problem with the agency as previous, and suppose that the implementing hypothesis optimal, which means T is equal 1, and the condition 70, which was liquidation condition, it's false also. And there exists a twice continuous differentiable solution to F to our ordinary definition equation 24, this one. And on this compact interval with the boundary conditions, it's important to set up boundary conditions such that the condition 50 it's a second order it's a second order conditions also holds. F prime of W is bigger than -1, which is the marginal cost. Then we have two cases again. If W belongs to this interval, Then the value function, the optimal sensitivity, and the worst case density generator. We consider these three conditions, and the contracts again pay a non-negative or the continuation value to the agents, who the continuation value follows from this dynamic, from the dynamic unity, from the last preposition, where t is between 0 and tau. Tau is a terminal time, stopping time. So the optimal payment is still the same as 21, and the contract determines at the stopping time. Yeah, that's also logic. And second case, if the continuation value of the agent is bigger than payout boundary, so the value function of the agent, the value function of the principles will be this plus this, and moreover, the principal also pay this amount, as we see, immediately to the agent, and the contract will continue with the new initial value payout, with the new initial value for the agents. So let's see what are the differences between this proposition and the first base case proposition. In the first base cases, the incentive constraints requires to this condition. That's why we didn't consider it. And the trade-off depends on the choice of the optimal sensitivity. Yes, a larger optimal sensitivity should provide incentives to the agent, but the larger the volatility terms of the optimal sensitivity of the continuation value, the large chance of liquidation. In finance, we say that like a higher volatility or diffusion term, the higher the risk, the higher the risk. Yeah. So it's the same principle as here. So the optimal achieves this amount if the principal value function is concave, and this lower boundary doesn't always mean depends of the model ambiguity. We see. Let's see why. Under which situation may the optimal sensitivity exceed the lower bound? We have 3 points listed here. The principle is more concerned about the inefficient. For lower value of the continuation value, the principle is more concerned about the inefficient liquidation. Therefore, the optimal contract will serve the optimal sensitivity at lower bound. And for larger continuation value and closer to payout boundary, the principle is more concerned about the model uncertainty. In this case, he provides the agent more incentives so that this condition satisfy. And we see that from this, the agents over incentivize if its continuation value is high. Now we have some graphs. So our first graph has 2 curves. Above curves is a value function for the first base case or the first base density generator with the payout boundary W bar FB, and the lower curve is a value function for the robust contract with the agency with the payoff boundary W bar. So the optimal sensitivity change the value at the payout boundary on W hat, After here, we see it's changed to what? And as we see, both curves are concave. So in second figure, we have two subgraphs, the incentive, the optimal insensitivity, and the worst case density generator. On the left-hand side, subgraph show that there exists a cutoff value W hat such that the optimal sensitivity reach payout boundary sigma lambda. It's 1. And on the right hand side, the worst case density generator on the left hand side graphs is the worst case density generator increases with the continuation value, as we see for good. It's increasing, yeah. Intuitively, the principal's aversion to model uncertainty leads to his pessimistic behavior. Even the worst case density generator is negative. And third graph consists 3 subgraphs. First, a value function. The principal value function subjected to the continuation value and optimal sensitivity and worst case density generator for robust construct with the agency. As we see, the value function may be concave in this region. So we will now consider a Bellman-Isik condition. Why we should consider this condition in our model? As we see in graph or in verification theorem also, the value function is globally concave. It's not globally concave, therefore the Bellman-Isik condition might not hold in those regions where the value function is convex. In this, so since the Bellman-Isik condition doesn't hold, then the exposed Bayesian interpretation cannot be applied, and the extremization order cannot be exchanged while optimizing. What we mean by extremization order, when we had our first HGBI, we say that we have 2 possibilities, either solving with respect to H first or with respect to phi. So here we said if we change or if we solve it with respect to phi first, our solution to ordinary definition equation will be infinity. Therefore, the extremization cannot be changed. So assess pricing. We now try to use our optimality, our contract optimality. So we now use our contract optimality can be implemented in debt reserves and liquidity. The capital structure consists of the cash flow empty with interest rate and coupon payment and the regular dividends. So the cash reserve dynamics can be consist of the cash reserves dynamic of the cash flow and the dividend and the inside dividend at psi with the initial value, where psi is a coupon, consists of coupon, outside dividend, and special dividends. So the special dividends, this term can be equalized to this term. It's it's okay. So on special dividends had slightly property can be only paid only the dividend can pay only to outside equality holders and also can be negative, and their expected value is zero under the agent's belief probability measure PA, and dynamic of the cash reserves now can be written on the following with yes, and assess pricing. So to price the security using the principles pricing kernel, we defined area. The equity value per shares can be defined this equation, which we'll see how important this equation is, and with the terminal, with the optimal, with the terminal stopping time, it is a time of the liquidation. A terminal stopping time, or it's the liquidation term time. So the principal model uncertainty, our general specification generates a market price of the model uncertainty, which is H star of lambda MT, which is the worst case density generator. The first proposition in this section, it's a local expected liquidity premium under the measure PA is given by this equation. It consists of the worst case density generator and optimal sensitivity and cash and price and liquidity price, yes, and some parameters. So to prove this equation, we define the cash reserves as a set variable, which is involves the debt, value, liquidity price, and credit yield spread. And again, we apply our Gassonov theorem to this dynamic of cash reserves under the worst case belief probability measure. Actually, it's optimality. Yes, and we will obtain this dynamic. It's subjected to this three condition, which is optimal payment at worst case density generator, optimal sensitivity. So if we solve this equation with respect to liquidity price, we obtain our ordinary ODE can be written in the following with the boundary conditions, and we actually used the 5 steps again, yeah, like it's a sketch proof. And the bound price dt equal dt of mt satisfy the ODE and with the boundary conditions. And if we also solve with respect to time, like units per time, t of 0 is 1. And now we reach our summary. So this is a two-party contracting problem. Involves it's a contracting problem, involves at least two parties, say agent and principal. Then we introduce a model uncertainty to one of the party, then define the dynamic cash flow under the original probability measure. Since we have the jointly absolutely continuous probability measure, we can use the Gassonov theorem. We can use the Gassonov theorem for change measure and define an equivalent probability measure in order to define the cash flow under this equivalent probability measure. And then we try to get HGBI equation for this dynamic, which is a partial definition equation. And lastly, obtain a contract optimality. And in the last section, we have seen how to implement optimality to pricing assets. Thank you for your attention.